Right. So now that we had this little excursion through linear response theory, let us try and make contact with the original model we started with. We started with the Langevin model, and let us try to see if the results of the Langevin model match with those of linear response theory and if there is consistency between the two. And after we do that, we will then go a little deeper into the Langevin model itself or the generalizations of this model, look at a couple of physical situations and then take up the next topic. So the immediate program is to see how consistent the Langevin model is or its results are with those of linear response theory, which was a whole formalism that we developed. Now the Langevin model for a particle, a Brownian particle in a fluid, we wrote down a stochastic differential equation, made some assumptions about the noise term in it, and then derived quantities like the velocity autocorrelation, the equilibrium correlation functions. Linear response theory on the other hand was entirely in terms of correlation functions, equilibrium correlation functions. So the question is there a connection between these two? In the process, we should also take note of the fact that while we did the quantum case also simultaneously with the classical case in linear response theory, the Langevin model was completely classical. We never said anything about operators or anything like that. If time permits, later we will look at a quantum Langevin equation. But for the moment we are looking at it at a much more elementary level, and let us try to make contact with the simplest Langevin model that we looked at. So let us call this this has to do with the mobility of a Brownian particle inside a fluid. Okay. So recall that we looked at a single Cartesian component, and quickly to recollect what we had done, we said a particle of mass m satisfies a stochastic differential equation which is v dot plus gamma v was equal to 1 over m eta of t. But this was a white noise, Gaussian white noise with 0 mean and a delta function correlation. So eta of t was equal to 0 and eta of t prime was equal to some constant gamma delta of t minus t. Now we have been talking about what happens when you perturb a system. Now therefore the analogous equation would be to apply an external force to this particle. So some external arbitrary external force, so let us say 1 over m f external of t. So we have definitely taken the system out of equilibrium by applying this force here, and we would like to know what the response of the system is in terms of what is the velocity, average velocity, averaged over some given initial condition. So we computed that, we found that v of t average was equal to v naught e to the minus gamma t, that was my initial condition, plus 1 over m, a term involving the average of eta of t which was 0. So let us write that down explicitly, integral 0 to t dt prime e to the minus gamma t minus t prime, and then eta of t prime, and the average of this quantity was 0. So once I took average, this term went away, but this term persists now. So you still have plus 1 over m integral 0 to t dt prime e to the minus gamma t minus t prime f external or applied of t prime. There is nothing to average over it, it is a given force from outside, and that is the result here. That is the explicit result for it. Now one of the questions we want to know is what happens if I apply a constant force over a lengthy period of time. Okay. Now normally we would switch on the perturbation at minus infinity, that was what we did in the formalism of response theory, but now I want to simplify matters a little bit and say let us switch it on at t equal to 0, and let us do the simplest case, which is a constant force at t equal to 0. So, F external of t equal to F naught equal to a constant. What happens if I put a constant force on the system? Then this average V bar of t, F t bar, is V naught e to the minus gamma t plus F naught divided by m e to the minus gamma t, that is this portion, and then inside the integral you have e to the gamma t minus 1 over gamma. If I do this trivial integral, this portion goes away, so we can simplify it and write it in a little simpler form. So this is 1 minus e to the minus gamma t. Okay. Now we want the steady state response of this system. In other words, since we switched on the force at t equal to 0, we should let t go to infinity to get the steady state response, not the transient. This is the transient included here. Otherwise I should switch it on at minus infinity and see what happens at any finite time. It is easier to just let t go to infinity in this. So what happens is that V of t divided by F naught per unit applied force, the average velocity or velocity response per unit applied force, divide by this F naught, this quantity in the limit t tends to infinity is finite, and it is equal to 1 over m gamma. Now you would expect that, because physically what is it that you have? You have a fluid with some viscosity in it, some friction given by this gamma. You are going to apply a constant force. If the force keeps acting, constant force, just like a particle falling under gravity, the particle you start with reaches terminal velocity and then it does not accelerate anymore, because the drag force on it is exactly balanced by the external force on it. That is exactly what happens here. So that is why it tends to a constant, because this is now going to tell you what is the terminal velocity. Per unit applied force, it is given by 1 over m gamma. There is a name for it, this quantity. Definition of this, mu, mobility, the mobility, which in this model happens to be equal to 1 over m gamma. In general, if I have an arbitrary particle, an arbitrary model for it, we do not care what it is, I apply an external field, then the average or the steady state average velocity per unit external force is called the mobility of this particle by definition. Now we have throughout in linear response theory applied forces which are time dependent, which are sinusoidal with some arbitrary frequency omega and so on. So this corresponds to no frequency at all, 0 frequency, because I put this F. When I put in frequencies, then I have e to the minus I omega t, etc. So one should really call it the static part of it, or the omega equal to 0 limit of it. So let me call this of 0 in anticipation of the fact that this is happening at omega equal to 0. Because pretty soon now next I am going to ask what happens if the force were not constant in time but was sinusoidal with some fixed frequency omega. That would be the dynamic mobility as opposed to the static mobility or the frequency dependent mobility, which by now you would have guessed is a kind of susceptibility. This is really what is happening. So what we are going to actually look at is the dynamic mobility. But the static part is 1 over m gamma in this model. What we are going to do, linear response theory presumably will give us a general formula for this. So we got to go a little back and see how does this tie up with a general formula. Let us do the following. By the way, we can straight away make one connection here in this model, and that is the following. That connection is we know that the diffusion constant of this particle is k Boltzmann T over m gamma. So this is directly connected to this mobility via this relation. And as you would have guessed by now, this relation between D and the static mobility has nothing to do with the Langevin model. In the Langevin model, it happens to be D happens to be this and mu happens to be 1 over m gamma, but this relation between D and that should be more general, should really be more general, and we will see why in a minute. Meanwhile, let us look at the dynamic mobility. What would the dynamic counterpart of this be? Well, we go right back and say now let the force on the particle f of t equal to f naught e to the minus I omega t for some given omega. So let f of t be equal to this. All I have to do is to put that into this equation here and do the same integral. It's again an exponential integral, right? So what happens now, v bar of t this is again f naught over m integral again e to the gamma t and integral 0 to t dt prime e to the power because the force is e to the minus I omega t. I put that in here, this is f of t prime and I do this integral which is equal to v naught e to the minus gamma t plus f naught over m e to the power gamma t, sorry, e to the minus gamma t here, minus outside, and then inside is e to the I gamma minus I, sorry, e to the power gamma minus I omega, this is minus t minus 1 over gamma minus I omega. Right? And this simplifies. So let us put that in. This is minus e to the minus I, e to the minus gamma t, and this fellow becomes e to the power minus I omega t. Well, okay, one should really, if you have a real force, the response should be real, so one should say real part of this, and I go through the whole real part. But when we define the susceptibility, we defined it by putting a sinusoidal external force, f naught e to the minus I omega t, and I said when you are going to compute physical quantities, you are going to take the real part on both sides, etc. So we will do that after we do this integral. So now what happens? Now you can see that v of t over f naught limit as t tends to infinity. Of course, the oscillatory part has no limit. This fellow will remain e to the minus I omega t because that is cosines and sines that do not have any definite limits, they keep oscillating, but this term will go to 0 and so will this. And we do the same thing as before per unit amplitude, this quantity. This by definition is the frequency dependent mobility mu of omega by definition, okay. And what is that equal to? F naught e to the minus I omega t. Alright, so one should write this, let me write this in the following way. Tends, so let us write this as tends as t tends to infinity 1 over m gamma minus I omega times f naught e to the minus I omega t. So that makes it much clearer, right? So instead of just gamma, you had gamma minus I omega here. Now recall what happened when we did linear response theory. We said that if you start with a Hamiltonian H naught and then you go to H naught minus A f of t and this f of t was f naught e to the minus I omega t. Then the change in any other physical quantity, the perturbation delta b of t, this quantity was from whenever you switched on the force, etc., minus infinity to t dt prime well, how did we write this, up to t dt prime f of t prime phi ab of t minus t prime. This is what we had. And in the case when f of t was equal to f naught e to the minus I omega t, in that case for a single frequency we discovered that this quantity delta b of t was equal to chi of omega f naught e to the minus I omega t, chi a b. That is how we define this chi a b. And then we went on to say this chi a b is an integral from 0 to one-sided Fourier transform of a response function phi a b. But the first step was to say that if you apply a steady force at a given frequency, the steady response is also going to be at the same frequency, not a transient, and it is attenuating the external force, the amplitude, by this complex number chi. So if the force is the real part of this fellow, the response is the real part of this whole thing. The real part of A times B, and A and B are complex numbers, is not real A times real B. There are interference terms between the two. There will be a term which has a phase lag and so on, right, lag or lead depending on the kind of response. So that is what is happening here. What we have identified is exactly that. We have said that the velocity response, this should be V bar, V of t bar, is this function of omega multiplied by the applied force. So it is clear that the dynamic mobility mu of omega is equal to 1 over m gamma minus I omega in this model, and what kind of susceptibility is it? This is a generalized susceptibility, but the question is what are the variables? Chi, what should I write? Well, the force applied is a mechanical force. So A, this operator A in the present case is x, because if you take this as a potential and you differentiate with respect to x, the force is f of t minus the derivative with respect to x gives you f of t. So that was the reason for my putting a minus sign to match with this case, right. So it is clear that in the present problem A is equal to x, and what is B equal to? V, because I am measuring the velocity response. So it is clear that what we have computed in this specific model is xv, and that has turned out to be this quantity. At 0 frequency, when you put omega equal to 0, this is the static mobility which is connected to the diffusion constant in this manner. We have to check that out also as a special case. But we have all sorts of formulas in linear response theory for this guy. So the question is that going to match? Is it going to give us exactly the same result? But what was our general formula for the susceptibility? And this is going to be the consistency check. If you didn't know anything about the Langevin model, but we did linear response theory, then you are going to say chi xv of omega equal to integral from 0 to infinity d tau, put that symbol, e to the I omega tau phi xv of tau. That is what linear response theory defines a generalized susceptibility as, and we are doing classical physics. So what is phi xv of tau got to be? Remember that phi ab of tau was equal to beta times a dot of 0 b of tau. in equilibrium. We derived that because we started with Poisson brackets and so on, played around with it, used the canonical ensemble, and then we discovered in the classical case phi is just the correlation of this product, but not A but A dot, because there was a Poisson bracket with H naught which appeared here. So if you apply that blindly, it is clear that this must be equal to beta times integral 0 to infinity d tau, yes, d tau times e to the I omega tau times A dot is x dot of 0 v of tau in equilibrium, just applying that formula, which is equal to 1 over k Boltzmann T times integral 0 to infinity d tau e to the I omega tau v of 0 v of tau equilibrium. But we want to compare with an answer obtained from the Langevin model. So we have to put in here whatever we got from the Langevin model, from the Langevin equation, without any external force. But we already found an expression for this quantity. This thing here was equal to k Boltzmann T over m e to the minus gamma t for t positive, gamma tau. Pardon me? Oh, this is chi, sorry, chi x of omega. The kt cancels, the 1 over m comes out, and this is precisely equal to 1 over m gamma minus I, which checks with what we have here. Okay. So this is the magic of linear response theory. This we got by solving the Langevin equation in the presence of the force. We directly solved for the average value, blah blah, etc., and got this. But this we got without any reference to any external force at all. We just said if you want this susceptibility, which will tell you how the system's velocity will respond to some potential external force, when you apply it, it's given in terms of an equilibrium autocorrelation function in the absence of the external force. But that the Langevin model gave an answer for, and you plugged it in and you get exactly the same result as before. So this checks the consistency of the Langevin model vis-a-vis linear response theory. Now one can go one step further. We know that at 0 frequency this fellow was equal to that. But remember, independent of the Langevin model, we computed explicitly what the mean square displacement was, and we discovered that asymptotically for a Langevin particle, all we did was to exactly compute the mean square displacement in this case, and we discovered that we had to have d equal to integral 0 to infinity dt v of 0 v of t in equilibrium, and that is just an integral of e to the minus gamma t, nothing more than that. So this directly gave us k Boltzmann T over m gamma. Okay. But if I multiply this by e to the I omega t, then I get the mobility automatically apart from the beta factor. So this relation is a special case of the relation which defines the generalized mobility in terms of the velocity autocorrelation. And what's that general relation? It's precisely this quantity, that it's precisely the identification that chi xv is equal to mu of omega, and in the general case this quantity here is precisely what we have computed, namely this is equal to beta times an integral from 0 to infinity d tau e to the I omega tau v of 0 v of tau in equilibrium. General relation for the mobility independent of any Langevin model or anything like that. Yeah.
So but in this Langevin model it turned out to be exactly correct because of the fact that Langevin model itself was linear, right?
Yeah, of course.
Otherwise you would have had other terms in the exact calculation that you did for the model.
Linear in what?
Linear in V. the Langevin model doesn't have terms like v square.
Okay, he's got a good point. This is a deep point. It is true that the Langevin model doesn't have any term which goes like v squared, but tell me, where could it have had a v squared term? At which place could it have had a v squared term at all? It's a good point. Where could the v squared term have been? And yes, it is true, that specific linearity of the Langevin equation is what is making it consistent in this case with linear response theory. But where could it have been? Where could you have got a quadratic term or any other power?
The systematic part of the.
Exactly, in the friction part. You could have ended up in the friction part with a nonlinear term in that. And then it's so not obvious at all to do this. But we should still be able to say something about it, and that we will when we look at it as a stochastic differential equation with a drift term, specific drift term, and relate it to a corresponding Fokker-Planck equation. So we can say more, we will do that shortly. But yes, at the moment, yes. There is another generalization of the Langevin equation which retains linearity and which should therefore be consistent with this guy, completely consistent with this, not as simple a model, and that is the following. You see, we have throughout been saying that this Brownian particle is much more massive than the fluid particles in the molecules themselves. If you make the mass of the Brownian particle smaller, getting closer to the molecular region itself, what would you expect? You would expect that the velocity would start remembering more and more what its past was. You would start building correlations in this velocity which are missing completely in the Langevin model. We have just said there is a gamma here and that is the time scale of this particle, but now you are going to much smaller time scale, so you would actually start remembering collisions, and you would have to now include 2 particle, 3 particle 2 time, 3 time correlations, higher order correlations you would have to include. In any case, you would have to do that. One effective way of doing that is to say, I will bury all that once again by saying that the particle has some memory, the systematic part has some memory in it. So one way to generalize the Langevin equation would be to say v dot plus not gamma times v, but let us say some integral over its entire history dt prime gamma of t minus t prime times v of t prime with some memory kernel here, again dependent only on the lapse time. This equal to 1 over m a dot t plus external force if any, etc. That is one possibility. We have to examine whether it is consistent or not. It will turn out it is not strictly consistent with the white noise here, okay, the moment you have this, but you can still treat this as a model. You can put an external force here and ask what is the mobility. You can ask what is the generalized susceptibility in this case. What would you expect will happen? Suppose you just took Fourier transforms and did this, what would you expect would be the mobility in this case? You would have a gamma of omega, you would certainly have a 1 over m times gamma of omega. We will come to the notation in a minute, minus I omega as before, definitely. This is not gamma of t, it is some kind of transform, but because it is minus infinity to t, the whole thing will be like a convolution. So what will this be? A one-sided Fourier transform, precisely, it will be a one-sided Fourier. So let us give it a name. I do not want to call it a tilde because that looks like a Fourier transform. This fellow is anyway defined only for t greater than t prime, it is getting cut off here. So let us call it gamma bar of omega, where this is defined as integral 0 to infinity dt e to the I omega t gamma of t, a one-sided Fourier transform. So let me write this as exercise. Show that this thing here, by the way, is called the generalized it's called the generalized Langevin equation. It's still linear, but it's an integral differential equation. And it will lead to a dynamic mobility which looks like this. Okay. But you know, we've been saying this mobility is a susceptibility. And with our Fourier transform convention, this object, whatever be the mobility, cannot have a singularity in the upper half plane in frequency. So we have to check that out. Now in this case, when we found out that mu of omega, so in the case when in the ordinary Langevin equation, this was 1 over m gamma minus I omega. So here, where is this singular as a function of omega? Omega is minus I gamma. This is 1 over I, so bring it to the right side. So in other words, in the omega plane, you have a singularity here at minus I gamma, which is fine, which is what you expect a causal susceptibility, retarded susceptibility to be. Now you would have to do the same thing here and show that this fellow, the root of this, the singularities of this denominator have to happen only at omega equal in the lower half plane. Okay, it's not too difficult to show, but you don't know the form of this function except assume some reasonable thing that it dies down sufficiently fast at infinity.
And positivity is there.
And also positivity. You need positivity here. So assume there is a monotonically decaying function of its argument, positive, non-negative, and then it's sufficient to show that this singularity is actually in the lower half plane, okay, as it should be, as it should be. So at this level at least we are satisfied that there is consistency in this whole business. Huh? Now let's try a slightly harder problem rather than just the free particle. Look at the harmonically bound particle and see what happens. Again there should be complete consistency. So we looked at a case of harmonically bound particles. Let's see. This was the oscillator in a fluid. Now we did this problem by not explicitly saying it's a Langevin equation, we just wrote down the equation for the average position. This is a second order differential equation now. So we wrote x double dot of t, the average value, plus m plus gamma x dot of t, this manner, plus omega naught squared x of t. I have already taken averages over the eta, over the white noise. So what is left is 1 over m f external of t. And what did we do? We found the green function for this problem and solved this inhomogeneous equation using that green function. Right? That was like a response function, or it was like a susceptibility. So if you recall, we found that in this case chi of omega was minus 1 over m times omega squared plus I omega gamma minus omega naught squared. And the poles were in the lower half plane. There is an imaginary part which was essentially minus I gamma over 2, and then there was some part which depended on whether you had over damped or under damped oscillator or whatever. Right. What susceptibility is this, by the way? I should put subscripts here. Well, we again apply a mechanical force, that is how we got it, which is x. So A is x in this problem, and B was also equal to x. So we have essentially found chi xx of omega, and we inverted this transform to get the response function, right. So if you recall, we inverted this by saying the corresponding, this fellow by the way was the Fourier transform of G it is the Fourier transform of the green function exactly, and what was the green function itself? Gxx of omega tilde of t, what's Gxx of t was equal to a theta function of t times phi xx of t. The retarded green function, it's got a theta function inside, and the Fourier transform of that product is what gave us this guy. Okay. So what we have to do is to take the inverse Fourier transform of this fellow, and that gives us, it should give us a theta function as well as this. So this says theta of g, this quantity here is equal to 1 over 2 pi an integral minus infinity to infinity d omega e to the minus I omega t g xx, or let us put that in chi xx of omega. And we know how to do this integral, because in the omega plane there are two singularities at these 2 points. This is omega minus, this is omega plus. The contour of integration goes like this. When t is positive, you are compelled to close this in the negative lower half plane, so that this contribution would go to 0 and you get a contribution. When t is negative, you are compelled to close it in the upper half plane, and there is no singularity, so the answer is 0. So it pulls out the theta function automatically for you. So this thing here is equal to theta of t automatically, and then there is this 1 over m sitting there all the time. And if you recall what we got the solution of the underdamped harmonic oscillator in the presence of an external force, right, essentially. So this involves e to the minus gamma t over 2 sine omega in the underdamped case, where omega underdamped was equal to square root of omega naught squared minus gamma squared over 4. So that is what we got. So we can read off the phi xx of t now. Therefore, in this problem phi xx of t is equal to e to the minus gamma t over 2 sine omega u t over omega u. We put a tau here if you like, if it makes you happy, it does not matter, looking at it for positive values of t anyway, divided by m. Okay. Just a quick check. We already saw that the time reversal property of this guy was dependent on the time reversal property of the two operators sitting here. Is this even or odd? Well, we computed this only for t greater than 0. We should go back and compute for t less than 0. You get a mod here. Nothing is going to happen here at this point. So it is actually an odd function in this case, as it should be, because the parity of this fellow depends on epsilon x with a minus sign, because it is a dot and a. These do not change and this changes sign, so it has got to be an odd function, which it is in this case. So that part checks. Now what we need, however, for the mobility and the diffusion constant, we need the xv, because you are looking at the velocity response, right. So what is this going to be? Phi xv of t is equal to Is there a quick way of finding out what the xv is? You're going to put one more dot there, right, which means you're going to essentially differentiate once with respect to t. So you are absolutely guaranteed that this thing is equal to the derivative of this. So it's e to the minus gamma t over 2 over m omega u times, first you differentiate this guy, so it's omega u cos omega u t in this fashion. So that's this portion, then you differentiate this guy, so it's minus gamma over 2 sine omega u t. That's phi xv of t. Now what's the mobility, what's the diffusion constant therefore? What does linear response theory give you for this? According to linear response theory, this has got to be equal to beta times x dot of 0 v of t by linear response theory, right. So this has got to be equal to 1 over k Boltzmann t times the velocity autocorrelation in equilibrium. What's the diffusion constant? So what is the diffusion constant? This will imply that d equal to integral 0 to infinity dt v of 0 v of t in equilibrium, right, which must be equal to therefore k Boltzmann t over n. So let's get rid of this omega u, let's divide here, this goes, so that this is dimensionless. Kt over m, so I have to do the integral 0 to infinity dt e to the minus gamma t over 2 times cos omega u t minus gamma over 2 omega u sine omega u t. I have to do this integral. So for a harmonically bound particle, this is the exact expression of the diffusion coefficient. What does this integral give you? So it's k Boltzmann t over m times the cosine just gives me gamma over 2 divided by this fellow here, right. So it's gamma over 2 over omega u squared plus gamma squared over 4. And the sine part minus, there's another gamma over 2 and then an omega u divided by omega u times omega u squared plus gamma squared over 4, and this cancels against this, which is identically 0. You should be surprised. You're not surprised. You shouldn't be surprised. So what's happening? What's happening? This particle is diffusing on the x-axis, and because there is a potential, it's not translation invariant. The point 0 is special. It's in a potential half m omega squared x squared. So it's really sitting inside this potential. There's a spring which is bringing it back to the origin. So the mean square displacement will not diverge. It should not diverge. Remember that the diffusion constant is defined as x of t minus x of 0 whole squared is supposed to go, well, to 2 dt. So if you take the limit as t tends to infinity, this guy, this should be equal to d. That's the definition of the diffusion constant in one dimension. The mean displacement should go asymptotically like 2 dt, or if you divide by 2t, that should give you the coefficient of diffusion. That's turning out to be 0. So what do you conclude? There is no long range diffusion in this problem. The mean square displacement does not diverge, goes to a finite constant. And what finite constant can it go to? So this is out. The symptom that d equal to 0, this thing is a symptom of the fact that the mean square displacement does not go like t asymptotically. It could go like a lower power of t, but it's not doing that either. Okay. It's actually going to a constant. What would it go to? What constant can it? Let's take it in equilibrium, so it doesn't matter what your starting point is. What is this quantity for an oscillator? Yeah, because we know this. This is a quadratic term in the Hamiltonian, the free Hamiltonian. So we know that half m omega naught squared, x squared average, must be equal to half kt per degree of freedom. This is true. So it implies that x squared average in equilibrium must go to k Boltzmann T over m omega naught square. It does not diverge as a function of t. That is what is showing up here. It is explicitly showing up. So we sort of did this backwards, right? We computed the green function, we solved the problem with an external force for the average position, and then by a little simple trick I differentiated it once to get the correlation between the velocity and the velocity autocorrelation function. I did not directly compute it. So this was a useful trick. Notice that the differential equation that you have is for x, and it is a second order differential equation. So we did not really mess around with it. We did not write, if I had written an equation for v directly, I could have done this, but then the restoring force would have involved an integral. The omega naught squared x would have involved an integral, and I would have had an integral differential equation, which is a bit of a mess. So I circumvented that by actually computing the xx chi xx, and then I argued, or phi xx, and argued that phi xv is just one derivative. Okay. I leave you to go back and find out what the corresponding chi x xv is. Okay. So go back and find out, in this case, what the cross correlation is, position velocity cross correlation. So remember that you differentiate as multiplication by I omega and integration is division by I omega. So in this problem as well, there is complete consistency with, now we should be able to get these results not each time appealing to the stochastic differential equation, but by directly looking at what the probability distributions are like. So we need a connection between the two, and that is going to be the theme that we take up next. And I will not do that today, but let me just mention the result here, and then we will take it up in some detail next time onwards. You see, all the stochastic differential equations that we have been looking at, all the stochastic equations have been in one variable. For example, there have been equations of the form some xi dot equal to some given function of xi, could be linear, could be constant, we do not care. So some function of xi, it could even be non-stationary, although we have not looked at such cases. This is the systematic part of the force that we are writing down here, the drift that we are writing here, plus something which involves white noise, eta of t, and the cases we looked at where eta of t had a correlation which was gamma times delta of t minus t prime. We can make it a little more general. So let me write it in that language. You could have a force, a stochastic force which is of the form g of psi t, some other function of the variable as well as time itself, times, let us call this zeta of t, and this is a Gaussian white noise such that zeta of t equal to 0 and zeta of t prime equal to delta function of t minus t prime. I will subsume the constant in the cases where this is a constant in this function here. So I have a slightly more general case than what we had so far throughout. General in several ways. First of all, this need not be a linear function or a constant in xi. It could be time dependent itself. This the force, what's multiplying it, the amplitude of this white noise could itself be variable dependent on the driven variable, and it could be a non-stationary here. So we have a very general situation here. Such a process is called by mathematicians diffusion processes. When this is a Gaussian white noise, these are called diffusion processes. The usual kind of diffusion we are talking about of a physical particle is a very, very special case of it. And the relation I am going to talk about next would be to go from this thing here to an equation for the conditional density, probability density of the variable xi. So the idea is, can I write an equation for this quantity? The conditional probability density function. On the way we will make an assertion that this defines a special kind of Markov process, which is then completely determined once you tell me this quantity here. We write a differential equation for this called the Fokker-Planck equation, and then we will study its properties. Okay, so let me stop here today.